Okay, in this video we're going to take a look at using forces in circular motion. And basically, using forces in circular motion is exactly the same as doing forces for the types of force problems we've been working so far. The only difference is you have to make sure that you're following the sign conventions of the RTZ coordinate system. And the only thing to really keep in mind is that positive is going to be going towards the center of the circle. And if you take a side view, the z dimension, or that z-axis, what we would normally call the y dimension, that z-axis is going to be positive up and negative down. If you're doing a helicopter view, then if it appears to go up the page, you would say it's positive, and if it's going down the page, you would say it's negative. So we'll take a look at that as we get into this more. The first step is the same as always. You're going to draw your FBD. But I want to say something about this, and I know I've mentioned it before, and that is that when it comes to the FBD, there are two possible views. The first view is going to be a top view, or you may like to think of it as a helicopter view. In other words, you're looking down on the situation as though you were in a helicopter. So you don't see what's perpendicular to the earth. That's the big idea here. Okay, and examples of those forces would be the normal force and the force due to gravity, or the weight of the object. You would not see those, and we'll look at that more as necessary. The other type of perspective you can take would be the side view. And the side view is though you're going to be standing on the side of the road, on the sidewalk or something like that, and you will see forces which are perpendicular and parallel to the surface of the earth. But you don't necessarily see all the forces from any one particular view. Now, ultimately, in the end, it's going to be experience which is going to dictate which one you should use to try to diagram a situation. And if you find that you're coming up shorthanded, you don't seem to be able to solve a problem using the particular FBD that you drew, then try drawing it from the other perspective and see what happens. Of course, step number 2, we're going to write F net is equal to MA. And the thing to remember here when writing F net equals MA is that the acceleration is going to be acentripetal, and that when we're talking about circular motion, it's always non-equilibrium because of the changing direction. It does not necessarily mean that you're going to have a change in speed, but you are having a change in direction. So the acceleration is always going to be equal to acentripetal, and acentripetal we defined as v squared over r, or the square of the speed divided by the radius. It is possible, although we're probably not going to have any situations where we look at this because this gets into total acceleration, but if you had a situation where there was also a changing speed, then you may have to account for that in your problem. But like I said, that's not really something we're too interested in at this point in time, so we're largely going to ignore it. But just so that it's in the notes, for the tangential dimension, or along the z-axis, the acceleration could be equal to 0, which is usually the case, but it may also be non-zero, so it's non-equilibrium, and that's just going to be problem dependent. So just keep your eye open for it, but it's not likely to happen in the problems that we solve. And then step 3 is the same as always. Once you get your FBD set up and you write F net equals MA, then you're going to substitute the forces directly from the FBD into F net. And then lastly, you solve. Okay, so it's just the same as it's always been. There's really not any change. We just have to be mindful that the acceleration is now a centripetal acceleration, so we write it as v squared over r, and that when we draw our FBD, we can have two different possible perspectives, and that not all forces are visible from both perspectives. Okay, so let's take a look at a simple example now where we have a motorcycle which is going around an unbanked turn. It has a radius of 100 meters and it's moving at 25 meters per second. So that's really quite fast in a rather small circle, but we're going to go with it. And all we want to know is the magnitude of the friction force which keeps the cyclist moving in a circle. All right, so step number one, we're going to draw our FBD. And we have two different perspectives on this. Okay, so perspective number one is a top view, or the helicopter view. And if this is the turn in the road, looks something like this, then the motorcycle is located right here. And we'll even say the motorcyclist is moving in that direction. So that's the direction he's moving, up the page at this point in time. Then any force which is perpendicular to the surface of the earth is not going to be visible. All we're going to see are those forces which are parallel to the surface of the earth. And to help you understand which forces are parallel to the surface, let's take a look at the side view. And this is one that you're actually quite used to doing because this is what we've done in pretty much all of our force problems up to this point in time. Not all of them for sure, but many of our force problems we automatically take a side view instead of a helicopter view. And for the motorcyclist at this point in space, so here's going to be our motorcycle, we would have the normal force pointing up, the force of gravity pointing down, that would be the weight, and then going into the page is the velocity. It's moving into the page as it goes around the circle or into your computer screen. And that means that it's going to have a friction force which is pointing towards the left, because it's that friction force that keeps it moving in the circle. Remember, all the rules for identifying forces will remain the same. We have one touch, and that is the motorcycle with the ground. And so that one touch can give us up to two forces. One must exist, and we call it the normal force, and it's going to point perpendicular to the ground, which is straight up. And then the other one, which may exist, is friction, and in this case, it must exist. That way the bike can move around the circle. And that one's going to be pointing towards the left, because inertia is going to keep this motorcycle wanting to move in a straight line like that. And so it's going to need something pushing in from the right side to make it make the turn. And so when we look at the top view FBD, the only force we can see is this one. So right there is the force of friction moving towards the left. So this is the FBD we get from the top view. This is the FBD we get from the side view. And again, which one you use is up to you. Now, keep in mind that just because you've labeled three different forces in the side view, that does not necessarily mean that you're going to use all three forces. So again, experience is going to help you out a lot here. All right, so here's step number one. We've drawn our FBD. Then we go on to step number two, and in step number two, we just write F net is equal to MA. Now typically we would ask, is this equilibrium or non? And this is non-equilibrium. And it's non-equilibrium because we're constantly changing direction, so that means we have a centripetal acceleration. When we write F net equals MA, we have to identify which dimension is this for. Now, in all the stuff we've done up to this point, we had the X dimension, the Y dimension, and the Z dimension. But normally we only refer to the X dimension or Y dimension. Well, because we're using the RTZ coordinate system, we have to identify, is this the radial dimension, the tangential dimension, or the Z dimension? And for us, because we're talking about a force that, this is what we're interested in, friction. So because we're talking about a force which is pointing in the radial dimension, we'll identify that as the radial dimension. So finally, step number three, we're going to substitute our forces in for F net. And remember, we're only interested in the radial dimension. and the radial dimension is going to be the force of friction. That's going to be it. And then we write m times a. Now, real quick before we finish solving this, because we really are almost done, I wanted to point out what the dimensions look like in each of these perspectives. So in this perspective, the radial dimension is this, going left and right. I should do it like that. The z dimension, I'm sorry, not the z, the tangential dimension at this point in space is this. And we do not see the z dimension because it's perpendicular to the page, or perpendicular to your screen. Now from the side view, what we have is the radial dimension is still going to be left and right. We have the z dimension pointing up and down. So there's radial, there's the z-axis. It's perpendicular to the surface of the Earth. And the dimension that we do not see happens to be the tangential dimension, because tangent to the circle is going to be into or out of your computer screen. Okay, so let's go ahead and finish solving our problem now. So step number 4, it's all about solving. We want to know what the friction force is, so our equation is already set up for what we want, and now we just need to make our substitutions. So the force of friction is equal to m times acceleration, but we don't know what the acceleration is. So what we have to do is find it. So you go to your equation sheet that I've produced, you look at the column that says definitions, and you see if there's a definition for acceleration, which of course we know in this unit is going to be v squared over r. So we rewrite our equation as m times v squared over r, and checking off what we know and don't know, the mass is known, the velocity is known, and the radius of the circle is known. So the friction force is just going to be the mass, which is 300, times the velocity, which is 100, and that's going to be squared, and that's all going to be divided by 25. So you can finish solving this out for a final number if you wish. Okay, now, just remember our naming conventions. This is just a review of another video. Centripetal is the word we use for the positive direction. It's an adjective. It modifies the vector quantity itself. Okay, so centripetal just means I'm moving in the positive direction. It would be the same thing as saying north or east. Okay, that's what centripetal means. It's just it's a way of dealing with the positive direction when you're talking about circles. If you say centrifugal, then that simply means the negative direction, and that would be equivalent to saying west or south. Okay, so all we're doing is describing in which direction does the force point whenever we use centripetal or centrifugal. Now, I want to just caution you, centrifugal is something that you're hardly ever going to use. We don't really want to emphasize these terms. In fact, I prefer not to use them much at all because they tend to cause so much confusion. Nonetheless, centripetal just means the positive direction, which is towards the center of the circle, and centrifugal means the negative direction, which means away from the center of the circle. So what I'm going to do is draw one more scenario. I'm just going to modify this scenario just a little bit to give you some concept of what I'm talking about when it comes to centripetal and centrifugal. So it's going to be the same motorcycle going around the same turn, and I'm going to draw the side view FBD. Well, actually, I'll do it on both of these FBDs, and I'm going to use an orange color to represent what I'm going to do. Now, as the motorcycle is going around the bend, just the way it is currently, a gust of wind happens to be blowing from the left towards the right. So we get some wind blowing. and that wind is going to push against this motorcycle as he's riding around this turn. And so the force of the wind acting on the motorcycle is going to be in that direction. So I'll just call that the force of the wind. And over here, again, it's the same thing. This is the force of the wind. Same object, two different views for our FBD. Now, in terms of centripetal and centrifugal, what we have is this. The friction force is centripetal because it points towards the center of the circle, and the force of the wind, this happens to be centrifugal because it's pointing away from the center of the circle. This is the negative direction. So if I were going to have to set up this force equation for the scenario where there's wind blowing, then this is what I would write. So we're going to have F net is equal to MA. This was step 2. And then in step 3, I would substitute my forces from the FBD. Now I've got two forces in the radial dimension. Okay, remember, we're still in that radial dimension. So I've got two forces in the radial dimension. One is friction, the other is the force due to the wind. Now, the friction force points towards the center. That means it's in the centripetal direction, which is the positive direction. So I would write the force of friction minus the force of wind, because the force of the wind points in the negative direction in the RTZ coordinate system. And that's going to be equal to MA. And we know that A was equal to V squared over R. So we would get, as our final equation solving for friction, we would get the force of the wind plus mv squared over r. But again, the whole point of this line of discussion is that the force of the wind is in the negative direction, which makes it a centrifugal force, and the force of friction points in the positive direction towards the center of the circle, which makes it a centripetal force.